In this video, I want to have a look at some trig problems that involve us using the sum and difference and double angle formulas. So what I've got up in the corner here are the three formulas that are given to you on your formula sheet. Now we're going to use those in solving all of our problems. So we're just going to jump straight into a question. Our first one asks us to find the exact value of cos 75 degrees. Now, previous to learning these, we could only find exact values if our ratio was to do with 30, 60, or 45 degrees, or some multiple of those. But what we can do now is we can break these numbers down into the ones that we do know, so our 30, our 45, and our 60, and then use our formulas. So we know that cos of 75, we could write that as cos of 45 plus 30. And once we know that, we can then use this formula here. So that means we're going to have cos of 45, cos of 30, minus sine 45, sine 30. And we do know all of those exact values. So cos of 45 is 1 on root 2, cos of 30 is root 3 on 2, minus sine 45 is 1 on root 2 as well, and sine of 30 is a half. So now if we simplify those down, we'd have root 3, not root 2, over 2 root 2 minus 1 over 2 root 2. So bringing that together, we could have root 3 minus 1 over 2 root 2. And we always want to rationalize our denominator if we can. So we're going to multiply top and bottom by root 2, which means in the numerator, we're going to multiply each term by the square root of 2. So we'd have the square root of 6 minus the square root of 2 over, and if we multiply down the denominator by the square root of 2, this would turn into a 2, so we'd end up with a 4 on the bottom. So the square root of 6 minus the square root of 2, all over 4. Our second question asks us to find the exact value of sine 90. Now sine 90, I like this question because we already know that that is equal to 1. And we learned that when we looked at the unit circle and when we looked at the graph of sine. But I want to have a look at it anyway and show how we can use this formula to prove that in a different way. So we could break that 90 down in two different ways. So we're going to solve this problem twice and show you that it works both times. So we could break our sine 90 into sine 60 plus 30, which would then, if we use this formula here, give us sine 60 cos 30 plus sine 30 cos 60. And we know those exact values from our triangles, so we'd have root 3 over 2 times cos of 30 is root 3 over 2 as well, plus sine 30, which is a half, times a half. Now that's going to give us root 3 times root 3 is just 3 over 4, plus a half times a half is 1 over 4, and 3/4 plus 1/4 is 1. So that's breaking it down into 60 and 30, but we could also break it down into sine of 2 times 45. So this time, instead of using this formula, we're going to use our double angle formula, which we looked at in our last video. We could put it in there as well, and it would still work. So we're going to end up with 2 sine 45 cos 45, which is going to give us 2 times 1 on root 2 times 1 on root 2. Now, if we multiply the 1 on root 2's together, we'd have 2 times a half, which is just 1. So that's a couple of different ways of proving that sine 90 is equal to 1. Our third example asks us to write tan of a minus 45 just in terms of tan a. So that means that we want to expand this out using this formula here and then simplify it down. So tan of a minus 45 would give us tan of a minus tan of 45 over 1 minus tan a times tan 45. Oops, sorry, that one should be a plus there. Simplifying that down, we know that tan 45 is just equal to 1. So we'd have tan a minus 1 over 1 plus tan a. Our last example asks us to write sine 3 theta in terms of sine theta. So what I'm going to do first is I'm going to split that sine of 3 theta into a sine theta plus 2 theta. So we've got two angles added together, so I'm going to use this formula here to expand it out. So we're going to have sine theta cos 2 theta plus cos theta sine 2 theta. Now I want to expand it out a little bit further, so I'm going to use my double angle results to expand this term and this term. So that's going to give me sine theta, and cos 2 theta would give me cos squared minus sine squared. So we can have cos squared theta minus sine squared theta, plus cos theta outside of, and sine 2 theta would give me 2 sine theta cos theta. So expanding out both of those sets of brackets, I'm going to end up with sine theta cos squared theta minus sine cubed theta plus 2 sine theta cos squared theta. So this first term and the last one are like terms because they've both got a sine theta and a cos squared theta, so I can collect them together. So I'm going to have 3 sine theta cos squared theta minus sine cubed theta. So the problem at the moment is I only want sines and I've still got this cos squared. But we know from our trig identities that cos squared is equal to 1 minus sine squared. So I'm going to replace that. So we're going to have 3 sine theta outside of 1 minus sine squared theta minus sine cubed theta. Again, expanding out the brackets, we'd have 3 sine theta minus 3 sine cubed theta minus sine cubed theta, still on the end. And then I can just collect my like terms with those last two. So we're going to end up with 3 sine theta minus 4 sine cubed theta. That's having a look at using our sum and difference and our double angle formulas to solve trig problems.